Okay everyone, I know you want to see another one, so here we go. Large old plasma screen. I don't even know if this one has digital freeview, to be honest. Well, I'm not even sure how old it is, and all I can see, it came to me like this without the back on it, so I don't know what model it is either. It says DS on the front, so whether that's what was known as Dick Smith, not sure, but all the internals appear to be Samsung. So yeah, issue is it won't turn on. I've already pulled the power board out of it after doing a quick basic check, and I'll show you what I did. And yeah, I'll see if I can find a date code on one of the chips maybe. Well, the sticker on the plasma panel says 2006. That's good enough for me. Ancient, but hey, yeah, if we can make another one work and keep it off the landfill, it still has enough inputs to be useful. The last one fooled me. I thought it didn't have HDMI when it did. This one really doesn't look like it has HDMI. It's got DVI and RGB and your RCAs and so forth. Very basic. So anyway, let's have a look at the power supply and I'll show you where I'm at. Oh, wrong side of the board. Yep, I was just checking the main input caps to see that they were discharged, and they are, and I've got a funny feeling maybe they were never charged to start with, but anyway, very big board, and first point of interest, of course, with it doesn't even have a standby light, so that's a sign there at the moment. We need our 5-volt standby supply for the brains of it to sit there idle and at least respond to a on signal. So this connector along here is that's got our VS on control. So obviously it's got VA and VS lines, or VS and V. What are they going to have in this one? Yeah, VS and VA. Yeah. Obviously the ability to turn them on and off separately. There's a relay line. Now maybe when we've also got 5 volts and 3.3, so perhaps when the CPU gets the go signal, it sends a command, a signal to the relay to turn on, and then everything probably fires up. But I can almost guarantee that, well, here's the AC in, and I've got a bridge rectifiers on here, some input chokes, and looks like possibly a lot of our switching stuff on here for some of it, and our main reservoir capacitors over the back. But yeah, bet your bottom dollar, here we got another little bridge rectifier and a capacitor, transformer. Almost guarantee that this is going to be our 5-volt rail, our standby rail. This will be running all the time, and we have a capacitor with a bulgy top on it. So we need, I guess, first to look at why we have no 5-volt. I'm going to be starting with this circuit in here. Now that's probably why the main reservoirs had nothing on them. This has its own reservoir, and the relay was never told to turn on, so everything is quiet. We could probably force the relay on and see if we get our other rails up, but I won't bother with that. We'll just start our focus on here, see if we can find anything obviously wrong other than that capacitor, of course, which may be all it is. Really. Yeah, so what have we got? We'll check out the value of that. It's a 1500 microfarad at 10 volts. Let's see what I've got in my pockets. Of course I've got everything, but I've got a 1000 mic here, and let's have a look. It's actually got a section down here in the silk screen that lists all the voltages and how much current they supply as well. The 5-volt line it's got there, it's 5.2 at just over an amp, so sure is a sort of a hefty line there, but I think 1,000 microfarad, at least to get a standby light on, should be plenty. We could always up it if we have issues with it. We could put a bigger one in later, but we do need to see if this thing's worth repairing so we can replace stuff as we go and get a feel for what's happening. But we'll pull that one out and see if it even has, where's the thought, see if it even has what sort of value it is. I'm pretty sure it's completely naffed. So we're down, here's our circuit here. I really should probably check that reservoir cap there just to see. I'm sure it would have bled off by now because it's been unplugged for a while, but that should have had power on it as well. We're at 500 millivolts. And do we have our own fuse for that one? We've got a main fuse in. Should probably make sure that we actually have a path through to there without interruption, and that it was actually getting half a chance to start up. Alright, so here's a basic idea of what we're looking at, and we've got our AC comes in. It goes to two places, but to get through to the 5-volt supply, it comes through its own fuse. So we need to check that. Comes through a thermistor, and that's just goes really high resistance when it gets hot as another form of protection. So sort of an overcurrent. Yeah, if the fuse doesn't go in time or something else goes wrong, that's also there. Bridge rectifier, and our DC out. There's our main filter cap, and then into the switching transformer. Now ignore that little line there, that was supposed to happen, but then it comes out. We've got our negative rail, and the other side of the transformer goes to a single little chip, which looks like it does all the control for that and all the switching in one package. So we need to make sure that our path through to the bridge rectifier is okay, that the bridge itself is okay, and if that's all okay, we need to start looking at the chip to make sure it's functioning. Of course, we're going to put that other capacitor in and see where we're at with that. It's likely that chip has failed. It could be something in the feedback circuit, which I don't believe is an opto in this case. I think it's just another winding off the primary. And yeah. Oh no, found the opto. Never mind, cancel that. There is an opto off the secondary, so need to make sure that's okay. And yeah, all right, let's remove that cap and see what that does. So here, just briefly, it's double-sided PCB, but we've got our phase coming down through to here's our fuse here. So it comes down on the other side through to here, through the fuse, through the PTC thermistor, and into the bridge rectifier, and our neutral line buzzing up on the underside. And then this is our positive and negative that come over to our cap on the other side, obviously, and off to, here's one side of the primary winding, and the other side is the negative side off to, here's our IC that controls it all. And of course, this being the secondary side here, we have a line off here to this opto coupler, and you can see that trace coming back down to that IC as feedback, so it knows what it's doing. Right, let's start with that capacitor, as it's obviously the most problematic thing. Actually, what I'll do, just to prove the rest of it's all right, we're in resistance mode there. So if we go from our fuse to, I've already traced it out, phase up there, so that's okay. It's getting to the fuse, then across the fuse, that's all good. From the fuse across the thermistor, that's 8 ohms, which I think is pretty acceptable. And of course into the bridge rectifier. So let's pop that into diode check and have a look at the bridge there. And I'm going to be going from positive lead on the anode out to, hang on, I'm not sure what way I'm looking. Let's have a look at that now. It must be negative, so we go positive. No, there we go. We've got our half volt drop, and then we go the other AC pin through to positive. That's our half volt drop there, and then we switch leads and we go negative through to or positive on the negative lead, anode through to the AC. There's our one there and other one, so it looks like half a volt across all of them. They're happy, and that's good. And of course, if we can do a resistance check across the main capacitor, but I'm pretty sure there's no issue there, and yeah, there's no overload there. Cool, right, let's swap that cap out. So, nice dirty way to do this. You could use a solder sucker and whatnot. If you heat the one leg and then pull, just push onto the side of the capacitor. So what I'm doing is it's up through the board like that, and I'm just levering it away from the board slightly, which is going to cause the pin to come through the board. And you can do that on each side one at a time. Just make sure it's nice and wet and just work it nice and slowly, because if it's not fully molten before you start doing it, you can pull the little through holes, but I don't think this one is connected on the other side, as there are a couple of large traces on this side, so I don't think through holes are going to be an issue for us. Don't forget to note the way it came out, although it's likely marked on the board and we should be able to figure it out anyway. There you go. Oh yeah, alright, so down in the gap there, so the negative is connected on both sides, but yeah, give it a wiggle. If it doesn't feel like it's going to come, don't really tug on it, and you should be okay. We can use wick or a solder sucker to clean the holes out with. Yeah, nothing else really untoward looking. Let's see what this says the capacitance of this is. That's going to take a few seconds to figure it out with the larger sizes. There we go. Our 1500 microfarad cap is now 38 microfarad, so she would have been struggling to build up the 5 volt rail, especially without horrible noise on it that would have been upsetting everything. So yeah, I think our 1000, even though it's slightly underrated, is gonna get us started in the right direction. Clean out the holes left, and it's always good to add a little bit of solder. It can make it easier to suck through. So this is our positive side, and maybe just have a really hot iron, or make sure that it's hot enough for it to have flowed through the board, being double-sided. And I missed that one. All good fun. I really should buy an iron with a built-in solder sucker. Really would make life a lot easier. Okay, I don't do this all the time, I suppose. Solder wick would be useful too. Okay, we've got that one in, and I'm actually out of solder wick. I think I need to go get some more. I'd also noticed on this board, one end of it had gotten really warm, and the solder's starting to give. So while I'm here, before I put this thing back together, I'm just going to add a bit of fresh solder to some of those spots, a bit of preventative maintenance. And sometimes that really old solder is really hard to get molten again. Find the solder doesn't stick to the pins properly, or the pad. Horrible stuff. Lead free. Now I'm going to be nice and dangerous here, and I've just soldered a lead directly onto the board, and we'll just plug it in and make a quick measurement, see if we've got our 5 volt back. and hopefully it was that easy. I really hope that drive main switching IC hasn't failed, but nonetheless, given its age, should be able to get hold of one. One thing I'm having trouble with getting is YSUS driver FETs for only a 4-year-old model at the moment. So yeah, it's a bit of a pain. I might be able to find some online, but two of them have numbers that are pretty much unobtainium. I can't find a data sheet or anything anywhere on them. So yeah. Anyway, mind your fingers, and we'll plug it in and take a measurement over here. See if we got 5 volts. Well, I can't hear anything. Of course, it's not under load, but sometimes you can hear the supplies oscillating a little. Shall we see if we have our voltage on our main filter cap there? I'm pretty sure we will. So if we just check across there, we should have 310. That's good. And now if we go to ground, and here's ground, and our 5 volt there, and we still have nothing. That's not good. So this thing is not starting up. Why is he not starting up? Well, you can see fluctuations there. You might be able to see the top of the multimeter. There's a bit of a fluctuation, like it's trying to start up and it's failing. So that's interesting. If we put it on AC, we might even see something like something that's 16 volts. Little fluctuation. Okay, let's see what comes on the secondary there and what's going on. Okie dokie. So let's measure across our cap. Now that the main one's discharged, we can unplug it, of course. Don't just rely on the switch on the wall, and we'll just measure across the cap there and just see if we have an okay resistance, that we're not trying to feed a short circuit or something. 48 ohms. Oh yeah, 5 over 48. What's that going to give us? Well, I'd be figuring 100 odd milliamps, so nothing at all. Anyway, next I guess we need to look at our feedback and make sure that that's working, because if that opto's no good, then it's not going to know what level it's at, and it'll shut down and continue to, like we saw, shut down, try again, shut down, try again. So we'll just have a look in diode mode. Now the beauty of this is we have a whole bunch of the same optos side by side, so we can get a rough idea of what sort of measurement value we should be getting, because all they are is a diode on one side and a transistor-like junction on the other that gets activated by the light from the diode. So yeah, so what we'll do is go diode mode on the multimeter, and we'll go across the 2 pins that are on the secondary side there, and I'm going to do it both ways just to see what happens. So we've got 0.8 of a volt drop across that way, and 0.6 across that way, which is probably the proper way. If I look at this one, I've got 1.2 that way, 1.9 that way. I wonder if that's, let's just make sure they're the same way around, eh? No, they're in backwards. Alright, we'll skip to the next one, or actually we'll go, what do we got there? We've got 1. Of course these are in circuit, so the values are going to be not 100%, but 0.8 and 1. Gosh, it's hard to get a proper contact. No, okay. Let's try the next one along. That's definitely the same way around as the other one. That gives us 1 and 1.3. Yeah. So we'll check the other side and just see if that gives us any sort of a reading, because we should have a reading on both sides, and at the moment I'm getting nothing on the other side of the opto there, whereas if we check these ones and that one there, well, that's only going to go that way. That's going to give me nothing as well. I always thought you'd get a reading off those. I need to brush up on my opto theory. When you're getting a reading on all of them bar one, or actually two, there's another one there that I don't seem to get anything on. Where was it? That one there doesn't seem to be giving me anything on the other side. So that's all very interesting, especially when all the rest of them do. That one there, and not that one. There was that one. Yeah, what way around are they facing? That one. So 3, 4, and second to last one there. So that one's the same way around it. I've got 0.6 on the other side there, and I've got 1 on that side. As I said, they're in circuit, so they won't be all the same, but still you should get something on the other side. And the other way, I suppose, to do it is to look at the voltage, because the voltage is varied, and that's what gives it its feedback. So if I plug this thing back in, and of course being on the secondary side, we need to use the main reservoir cap negative as our ground reference. You can't go using the chassis or whatever from the secondary side as ground, because they're completely separate grounds. So the primary side ground for any circuit on the primary side has to be your main, well, the main filter cap's a good reference. That's where it all derives from. So I will just flick it back on. Out of curiosity, we shall take a voltage reading, and you'd expect to see some voltage there, something fluctuating, to show that it's actually working and behaving like an opto should. So right, remembering that things are alive now, so watch your fingers, and we'll go negative there, and we'll go onto there, and we've got nothing there, and we've got nothing really there, nothing really. On the secondary side, we've got a fluctuating voltage, which we'd expect to see, and yeah, so there's a fluctuating voltage on the primary side with there's another one there, which is our other opto, that has very little, nothing happening on the output as well, or at least something seems to be happening, but this side is dead as a dodo. Alright, I've just sort of traced out the rest of this drive circuit, and here we go. Okay, so this seems to be some kind of self-starting IC, and that as soon as we get our 300 volts across the cap, part of it's going to go through, well, all of it's going to go through through this diode here, and this, I mean, actually, I might be wrong about that. Anyway, it's still is self-starting to some degree, but what happens is there's a another winding on the primary side there. I've just tapped off that one. It seems to be its own winding though, but anyway, I've tapped off there, and what happens is we get voltage through this diode. There's a resistor and a small capacitor to ground. We have a Zener diode, which is a diode that breaks down at a certain voltage in reverse. So say it was a 5-volt Zener, for example. If the voltage at the cathode here was greater than the threshold, might be 5.3 or something, or whatever. If it was, say, a 6 volts, then it would start to conduct through to ground, forcing that to remain at 5 volts. Of course, the higher that voltage goes, the more power this dissipates, and they're only rated to certain amounts. So the rest of the circuitry has to be designed around the fact to, and hope that it doesn't actually exceed much by the set voltage of the Zener, but that's generally a protection thing, so that on a huge over voltage there, they often just short out and clamp the rail to ground so that you cannot damage the IC. So that's what that's there for. Then there's our a larger capacitor here, which supplies the voltage and current needed for our switching transistor. That comes into pin 4 of the transistor of switching IC, not transistor, but yeah. So all of the pins on one side are connected through to our primary winding. They switch through to ground. Pins 1 and 2 go to ground. Pin 3 is our feedback pin. So I'm not very good at drawing schematics, but it's a bit convoluted there. But as you can see, we've got power comes up through a resistor to one side of the optocoupler. I know I've drawn that wrong, shut up. And the other side of the optocoupler comes back to our feedback pin. So the secondary side of the optocoupler, just a photodiode, emits light, turns this on. The more that turns on, the more voltage is going to, or current is going to come back through to here and tell this thing whether it needs to switch harder to get more on the output or switch lower to get less on the output. That's that. So knowing that this isn't starting up, we need to make sure that the power supply to itself is okay. And I've taken a measurement on this capacitor, and we have nothing. And I took a resistance check, and we have 2 ohms to ground, and that's far too low, hence why everything's shutting down and misbehaving and doesn't want to go. So yeah, we need to find out why. We've got a short to ground, a very low resistance to ground, and I think the easiest way on something like this is probably just to start pulling stuff and testing it. I would start with the Zener myself, given its role in the circuit. That's likely point of failure. Could be this little capacitor up here. Could be. I didn't have a close look at it. It may be a tantalum. And they are known to short under failure. And the other thing is the chip. And if the chip's shorted, well, we're screwed for now, at least. Maybe forever. Who knows? But interesting. What side did we not? We had a reading on the secondary side and not on the primary side of the opto as well. So whether we have had sort of a bit of a surge, power surge, and it's shot through and blown the opto along with the Zener, and hopefully not the IC. Who knows? But let's start with lifting one leg of the Zener off the circuit and testing that. So just quickly in practice, this is what this all looks like. Here's our main filter cap, here's the chip. Here is the primary side of the transformer, and these 2 pins here are the winding of interest. On the other side of the board it comes off. Here is that first diode that it goes through, and it comes from this side of the diode through to here. And then we've got our resistor and capacitor to ground, the first ones. This trace then follows around. Here we have our Zener diode, which goes from that line, this side goes to ground, and then our main cap that supplies the bulk of the current requirements for the switching transistor into pin 4. And this Zener is what we're going to check first. So I've just straightened the leg up on that and sucked the solder out so that it's sitting freely inside the hole, sort of made it central on the hole, and it's a bit tricky to remove this one because it's under a big dollop of goop that appears to be holding the heatsink on top of that chip. So firstly what we want to do is make sure that it's not connected to that hole. So I'm just going to touch the pin and the trace here and make sure that that's not touching, not creating a short, yeah, it's pretty good. I'm happy with that. And then I'm going to measure here and there. That seems okay. Then I'm going to measure there. Don't know what way it's sitting in the circuit. Oh, that says shorted. Why does that say shorted? Did I not have a very good connection on there before? Let's try that again. Here and here. Ah, yes. That's saying shorted. Maybe I've got it back in the hole. No, not connected there. Shorted. I think we've found our culprit, at least part of it. So we need to get that Zener out, find out its value, and replace that, and go looking for any other problems. But what we will do is do a resistance check across, and we go from ground to our voltage rail and see what our resistance is with that Zener out. No, it's better, 28,000 ohms. So that Zener was pulling that rail to ground, which meant this IC was not turning on, and therefore we weren't getting our 5 volt standby. With any luck, I've mismeasured the opto and it could be alright still, but yeah, we'll get another Zener and see what happens. I don't want to turn it on without that Zener. As I said, the inrush from startup may be too much for everything, so we do need that there to limit that until it starts to oscillate, because then I think it will derive its own proper voltage rail from that. Because yeah, as I said, it's kind of its own secondary winding on the primary side of the transformer though, and in fact, I'll throw this out there. I think I'm right. So what's happening is, as our AC waveform is building up across here, sorry, as our DC is building up across here, it's creating a change in magnetic field, which is inducing enough voltage in this winding to kickstart this to start running, and then its own oscillating of that is going to keep that, because of magnetics and changing polarity and induced currents and so forth. So there we go. And there's the culprit. And the only markings on it is B30, so I reckon that one's going to be a 30 volt Zener, which means anything over 30 volts, or roughly thereabouts, is going to cause this to reverse conduct, and yeah, it must have had quite a higher surge, or it's just given up with age, I don't know, and it's just yeah, shot through the roof. I really doubt that the secondary cap that had bulged would have caused that. Really don't know, unless what could have happened is, with the lack of capacitance there, it may have been switching harder to try and generate the 5 volts, because without that that capacitor to smooth things out, it may have been switching harder to compensate for that, in which case the supply, which is based on that, off the other primary winding, may have gone higher, and the Zener may not have been able to cope over a period of time. Well, that's a theory. That's all one can have, but there doesn't seem to be anything untoward on the secondary as far as low resistance or anything, so I think we're going to be alright. We'll put that Zener in. Won't be able to get one till tomorrow, so you won't know it, but yeah, I have to wait. You get to watch it right away what happens, but I have to wait. I might just check some junk and see if I've got one. Yeah, we'll do that, but when we come back we should have a Zener to put in. Holy smokes, people, I just did a quick Google search and I actually found the schematic. If you want to have a look at it for reference, this is a Samsung board, model V4C power supply schematic, and yeah, I thought it might be a bit harder, so I didn't bother looking, but here we go. So yeah, as you can see, we've pretty much sussed it out, haven't we? But where's our zoom in buttons a bit? zoom in, and this is our power in, and it wasn't too far off the mark really. We've got, what have we got there? There's our input chokes and so on and so forth, and somewhere in there was a couple of relays, but never mind that. Here is our fuse for the, just put my hand on something, I haven't got it on the stand. Here's the fuse for our switching circuit there, our 5-volt supply. Here's the thermistor, and our bridge rectifier. Here's the main filter cap. Here is that chip that I mentioned, and we can see, if I maybe should zoom out a little. So here's the transformer. Here's there's one primary winding which is switching directly, and down here we can see that other winding I was referring to. Now here's that diode. This is the power supply for this chip. So here's that diode. Here's the first capacitor, resistor, our main capacitor, and the Zener diode. And the main reason I wanted to find the schematic was just to make sure that was a 30-volt Zener. Now we have MTZ30 is the exact part number for that Zener, so we can look that up and double check. But yeah, bonus material. So there's the rest of it, and the cool part is this is going to have the entire board on it's across 3 pages, but that is awesome, because if it's going to get a lot more complex, then we know where to look. But for the meantime, here's our standby supply, and we pretty much nutted it out. Oh yes, look at this. Here we go, hang on. This is what a opto isolator should look like. Not like my crappy little drawing. So yeah, this is the secondary side. We've got coming off our 5-volt line. Looks like there's another Zener there. Interesting. I will check that one, but that's on the secondary side. I don't think we've had an over voltage situation on there. So yeah, voltage through our diode lights this up, turns that on, gives us our feedback up to the IC there, exactly how I drew it before. And yeah, sorry, feedback pin 3. So yeah, how about that? Who needs a schematic when you can draw your own, huh? Yeah. Okay. Next time you next scene, if this is a show, I shall have a Zener, and we will pop it in and see where we go from there. Alrighty, it is now tomorrow day lunchtime. So I've just picked up a couple of Zeners. They're 80 cents each or so, so you know, why not have a spare? Probably never ever use one again in my life, but can't hurt to have one. So a little bit different looking. This one's a 1 watt, the other one was a half watt from memory. There's a 1 watt one, should be fine. Being a Zener, they go in with not, because normally your diode, you've got your current flow from the anode through to the cathode, stripe at the cathode. So Zeners go in backwards so that they you know, they don't start conducting until a reverse breakdown voltage is met. So let's clear out the hole for that one, and not hot enough. It goes through to ground. There's a great big ground trace on the other side there, so just give it a wiggle around. It helps encourage the liquid to flow through the hole better. It's being rather difficult. May be able to sort of push it through from the other side, or even sometimes you can use the pin and just sort of, oh no, here we go, push that through, get that wet and push it through. And if you give it a bit of a bit of solder on the end of it, let's clean that off so we can pull it back. and that cleaned the hole out with the pin of the diode. Wipe that off. It's going to let me have it. It's not going to let me have it. Come on. No, okay. Where is it? I'll just cut that end off, shall I? It's going to be shortened anyway. Right. That was a bit awkward to get through the holes, especially one end that's right up under the heatsink of this this IC. So yeah, we want to make sure that sits flat on the board so that the leg isn't touching the heatsink, although I'm pretty sure the heatsink's isolated anyway. It doesn't matter. Now, make sure we got that in the right way round, which we did because we looked before, and it is marked on the board as well what way round it goes. So there it is, tucked in down the bottom. There's the heatsink for our chip, and just tucked in down there. Right, shall we plug it in and see what happens? Everything looks good. Still don't think I hear it oscillating, but I don't know if I can expect to hear it oscillating. But no smoke. Let's check our 5-volt line there. Ground and 5. Oh, that's a shame. So maybe that optocoupler is not working, but we can see if we have a voltage supply on the chip. Yeah, on the chip there. What do we got there? Ah, 14 volts. I don't know what this chip's supposed to run at, but with nothing on the output, I'm almost going to say that, oh no, there's 5 volts there. What are you talking about, man? What are you talking about, man? Maybe this pin's not supposed to have 5 volts. It says D5V. Maybe it's our AC detect line that's supposed to have 5 volts or something. Nope. What about relay line? 3 volts on the relay line. Do we have 3.3? Nothing on 3.3. Okay, so well, that's good. We have got 5 volts on the output now. We just need to know where that goes to. Maybe it doesn't go to where I thought it went to. But that is the connector for the main board. Found it. Just follow the trace. Doi. Goes through an inductor through to VSB, V standby. So if we hook that, here we go. 5.2. Right. I think he's got it. Let's plug it back into the TV and see what happens. Alright, we had standby light, and very hard to show you, but leaning up against the wall we have picture. And that says no signal, but that's better than kicking the bum. So, happy days. That was all it was. And I've checked the 5-volt rail, and under load with it running, it's still 5.2. I think on the board there it said 5.3 was what it's rated to, was supposed to run at. So yeah, that's good under load. So our 1000 mic cap seems to be holding up. I'm pretty sure that's going to outlive the rest of the TV, being a big old plasma like that. I mean, usually on the plasmas, your YSUS drivers, all these ICs here have been known to fail. Although I'd read an interesting article that it's like a silicon or glue type insulation material that they stick all around the outside of each one can break down over time and become conductive, and it just destroys the IC because you've got your VS voltage on those ones. So it's the higher voltage, I believe. So Yeah, but and then also on these heat sinks here, you've got your driver FETs. You see some more on the board here. And they oscillate the panel between ground and VS in conjunction with the other side of the TV. So yeah, I'm currently dealing with an LG TV that has an issue like that at the moment. Those FETs are blowing, they keep blowing. Yeah, bit of a head scratcher. Anyway, thanks for watching. I hope that helps you understand your own circuits better and fault find what's going on with your issues. And yeah, it can, if you can't find a schematic, just sort of trace it out as best you can on a bit of paper. It might become clear as daylight as to what's going on. Catch you next time.